Okay, so I am. Hello, everyone. We are covering the last piece on VSEPR Theory today, which is the polarity and the intermolecular forces. I'm going to share my screen now so you can see the places where I am looking at. All right, the polarity and intermolecular forces is right here on van der Waals. Van der Waals forces are the same thing as intermolecular forces. So whenever I ask you which intermolecular force, don't say van der Waals, because that includes everything and it's not. All right, so let's go. Oh, and one other thing we're going to do is look at the properties of water, because it's very important since water is the universal solvent. All right. In order to be able to tell a polarity, we are going to go up a little bit and we're going to look at this. It's very simple. Polarity is a way to look at the partial charges in a covalent molecule. So a dipole moment is an imbalance in those charges that is produced by a difference, usually in the electronegativity of the atoms involved. Like right here, hydrogen and chloride. Hydrogen and chlorine, I'm sorry. Hydrogen is less electronegative than chlorine. So chlorine is going to pull those electrons in the electron cloud of hydrogen closer to itself, therefore acquiring a partial negative charge, which is denoted as a delta negative, and hydrogen will acquire a partial positive charge, and that is what a dipole is. When we're looking at how to determine if anything is polar or non-polar, all we need is a Lewis structure, because it depends on the molecular shape. If you do not have a molecule or a compound that has more than two atoms, because if it has two atoms, obviously it's electronegativity that matters here more than the molecular shape, because there would be no shape. All right, the next thing is how do we do it? Okay, so when you have a non-polar molecule, you will have symmetrical molecules in their shape, and they usually are. So are the dipoles. The dipoles are very symmetrical and they will cancel out. Now look at boron trifluoride over here. Boron is less electronegative than fluorine. Therefore, the electrons would be pulled closer to fluorine in all directions. But remember, dipole, this electrical charge imbalance is both magnitude and direction. So it's a vector quantity, and you need both magnitude and direction. And the magnitude is the same because it is the same atom that is involved. Both atoms are the same. And the direction, basically you would have to add these two up, and all of them, they would end up canceling each other. With, if you've ever done vectors in physics, you would know what to do. But don't worry about that. If you don't, that's fine. You will learn it later. Determining molecular polarity. Okay, so once again, if you're a polar molecule, you will be asymmetrical. That's the word that we're looking for. Asymmetrical, and they will not cancel. Look at this water molecule right here. This water molecule has a net dipole moment because the two hydrogens are attracted to the oxygen, and there is not a third thing that could cancel it. Therefore, the oxygen becomes partially negative, and that's where you remember this, because when we look at properties of water, this particular thing that I'm telling you right now will be very important. So look at how the hydrogen electron cloud is pulled towards the oxygen in both of these, therefore creating what is known as a net dipole moment. Therefore, the molecule is polar. Now, determining molecular polarity. So one of the things that you have to remember is when you do your structure, your Lewis structure, if you have any lone pairs about the central atom, or you have a different atom that is part of the atoms that are bonded to that central atom, then you're going to have a net dipole. So there are two conditions, and either one of them is met, then you have dipoles. One is the asymmetrical shape, which includes lone pairs, right? And the other one is the asymmetrical atoms, like CHCl3, for example. You have 3 chlorines, but you have 1 hydrogen. So normally, if this had been all chlorines or all hydrogens, this would have canceled. But since it didn't, because one of them is hydrogen and one of them adds to the down pull, the pull down of the hydrogen towards the carbon that's in the middle. The other ones are pulled from the carbon to the chlorine, because chlorine is more electronegative than carbon. All right, so that is how you know when your molecule is polar. So the next thing we're going to do is we're going to go to the next part on the module. Let me see if I just go back, would be easier. Yes. All right. Once we do that, we are going to go down to look at what are the types of intermolecular forces that we have. There are only, and let me make sure I've got the right one. The one that I like the best is the purple one. And I usually use that one rather than anything else. Okay, so here is not, this is not the one. See, this is not the purple one. Although these are good, don't get me wrong. They're both good. They both give you good information. This is not the one I wanted. Okay, so we're going to close this one and open the other one, because this is not it. Let me go back and go get that one. All right, so the next one that we were looking at is the intermolecular forces PowerPoint, which is the lower one, this one. All right, once we do that, we're going to download it. Hopefully this will work. It worked. All right, let's open you. Okay, there it is. This is the purple one. That's what I was telling you. All right, so intermolecular forces. What is that word? What does it mean? Well, inter is a prefix that means between. Like for example, when you travel internationally, that means you're doing travel between nations, right? Or international affairs, that's affairs between nations. Okay, so intermolecular means between molecules. So these are the forces that occur between molecules. There is a difference between intermolecular and intramolecular. Intramolecular is much stronger than intermolecular, because these are the forces that hold the atoms together in a molecule, such as bonding. So intermolecular forces, like I said, are much stronger. Are much stronger than inter. But if you look at how much energy, kilojoules, 41 kilojoules, it takes to vaporize, that means change the state of, right? 1 mole of water, that means we have intermolecular forces, because these are the attractive forces between the molecules. Whereas It takes 930 kilojoules to break all the oxygen to hydrogen bonds in a mole of water. Those are the intramolecular forces. Just to remind you, intra, if you think of IM, intramuscular injection, that means in the muscle, right? So that's in the molecule. Okay. All right, so generally, and this is the truth, mostly our intermolecular forces are much weaker than intramolecular ones. So how do we measure them? Well, we need to measure something that tells us how attracted they are to each other. For example, boiling point. If the boiling point is high, obviously they're more attracted to each other than not, because it takes a lot more energy to break them apart and become, to break the intermolecular forces and become more loose like a solid or a gas in this case, right? From a solid to a gas. All right, melting point is another one. Once again, from a solid to a liquid in this case. Delta H, which is heat of vaporization. We can also do heat of fusion and heat of sublimation, any of those. All right. It's interesting that without intermolecular forces, proteins would not be what they are. They would not fold. They would not do beta or sheets or alpha helixes. They do not do different sites where they, bond to the substrate. None of that, because of intermolecular forces. They are doing that. So they are, as you can see, they are responsible for crystal structures like the snowflakes. All snowflakes are different, they say. Well, that's because of intermolecular forces. Melting points, boiling points, and all of that, surface tension and density. All of these things do take a role in intermolecular forces take a role in all of those things, melting points, boiling points, all of that. And DNA too. DNA without intermolecular forces, which forms the disulfide bridges, and well, that's in proteins, and in the hydrogen bonds that hold the two sides of the DNA molecule together, this would not exist. We would not exist. We could not replicate. All right, so intermolecular forces there are four that we're going to talk about, and they are London forces or London dispersion forces. We call them LDF for short. Dipole, D-D, just for short. Interactions, that's when you have a dipole and it creates another dipole. In an ion dipole, you have an ion and it creates a dipole in a molecule. And then you have hydrogen bonding. And we will talk about these a little bit more detail here shortly. All right, the first one is London dispersion. London dispersion occurs between every compound, and they just arise because of the proximity that two electron clouds would have on each other. They would repel, right? So as they are repelling each other, they are distorting the electron cloud shape, and they're distorting it away from the other electron cloud. Therefore, you will form a positive and a negative area at that point. They're very fleeting, they're very short-lived, and it is also dependent on how large your electron cloud is. So if you remember doing the atomic radius, this is where it comes in. Atomic radius for fluorine is smaller than the atomic radius for iodine, because atomic radius increases going down and right to left on the periodic table. So if you remember these things, it's a good thing. And electronegativity is the opposite way. right, left to right and up, bottom to top. All right, so another thing that matters is how long the carbon chain is in the molecule. So in this case, there are more, see it says here, they increase polarizability if they have larger electron clouds. So longer chain have larger dispersion forces, which makes sense. All right, here's another one. The other thing is if you look over here, this is how easy it is to disturb the electron cloud, right? That's what polarizability means. So if you make something polarized, it is easier the higher the size of the electron cloud is, number one, right? So more electrons, therefore bigger electron cloud. Another thing is it's more diffuse, so that means it's bigger again. And they increase with the molar mass because the mass also increases with the size of the electron cloud as you go down a group, though. They don't increase going across a period. So just remember that. All right. So the next thing, see how the melting point will increase? That's because the intermolecular forces are increasing as you go down. From negative 182.5, which is cold, 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 to 171 Celsius. That's a lot of heat. All right. So is the molecule polar? We have already talked about that, but we did it in a way. So if you look at water, which is what this is, we have an electron lone pair of electrons, actually two. Therefore, this molecule is polar. So you would end up with a net dipole. This molecule right here, first of all, is symmetrical. Second of all, has no lone pairs in the central atom, which is carbon. So no dipole. Therefore, the dipoles would cancel and you would not have a polar molecule. Over here, SO2, definitely you have a lone pair, as you can see, and the molecule is not symmetrical. Therefore, you would have a net dipole, except this time it would be going down. And the molecule would be polar. The next one, this is methane. This one would not have a dipole because they would all cancel. Therefore, and the molecule is very symmetrical too. So you would not have a dipole. Therefore, no, it is not polar. All right. So now, dipole forces. You notice that what it says very clearly, it says attractive forces between polar molecules. So water actually attracts water, right? And water attracts other things that have a polarity. So it doesn't matter what it is, as long as it has a charge, water will be attracted to it, or any other polar molecule will be attracted to it. Therefore, when you have things dissolving, it is, remember, I don't know if you remember, but we said that like dissolves like. So basically, one of the things that you need to look at is the polarity of both molecules, the water, the solvent and the solute. And if they're both polar, then yes, it'll dissolve. If one's polar and one's non-polar, then it will not. All right, so right here, you can see that this is a very non-polar molecule because it's symmetrical. See how symmetrical that is? Whereas this one is very asymmetrical. Therefore, those molecules will definitely have a positive and a negative end. All right, the next thing to look at is ion dipole. Okay, so once again, ions are charged. So if you are doing as an ionic compound in water or in any other polar molecule, they will dissociate and they will go towards the positive or negative, depending on what ion you have. If you have a cation, it'll go towards the negative. And if you have an anion, it will go towards the positive. And you notice here, it says the larger the charge, the stronger the force. Okay. And here is a picture showing the ion-dipole interaction that is dissolving salt in water. And that is an ion-dipole interaction. These arrows right here are showing you the ion dipole. This is a negative. So of course, the positive end, which is the hydrogen, would be involved. Whereas over here, the sodium is involved with the oxygen of the water molecule, which is the negative end, since sodium is positive. All right, this is the last one. And hydrogen bonding is actually a very specific type of dipole. And what happens is an interaction between the hydrogen atom in a the hydrogen atom in a polar molecule that contains oxygen, nitrogen, or fluorine, which are very electronegative. Okay, so the hydrogen bond will form here. And that, if you remember over here in this picture, that's what these little dots are. See, they have hydrogen bonding between water because you have a hydrogen and an oxygen, which qualifies, and it's polar. All right, so they have to be polar. That's another requirement because NH4, for example, even though it has N and H, is not polar. Therefore, it could not do hydrogen bonding because it's not polar. All right. So like I said, it is a special type. Remember that you have N, O, or F. All right. And the crystals of benzoic acid have these long crystals, as you can see, and they stack in plane because this is the dispersion forces that you're seeing here in action. Now, to recap, London dispersion forces will happen in every single molecule, whether it's polar or not. So remember that. Let's write that down. And we're going to actually write this down because it is important to remember that we have a polar molecule. So here, let me put it in text form. So this occurs in polar and non-polar molecules. Okay. This one occurs between two polar molecules. So if the molecule is polar, then that's all it needs, right? This one occurs between an ion or ionic compound in this case, right? Or an ion, any ion would work too, and a polar molecule. So if you have a dipole, chances are you are going to, have this interaction happening. Now, if you're capable of doing it, we're going to write as yes. And this is a dipole moment between compounds that contain a hydrogen bonded to either fluorine, oops, then do capital F, fluorine, oxygen, or, okay, and that's to recap. So this recap right here will help you do our next activity. So let's go ahead and keep going with this. Now let's look at the properties of water. Let's clear all this. Well, actually, let's do a little practice first. And then we're going to go and do the properties of water. Okay, so I'm going to escape this. It's not letting me escape. Okay, there we go. All right, now we're going to look at properties. Well, these are some of the properties that are caused by that, but since we're going to look at properties of water, we're going to be talking about both surface tension, adhesion, and cohesion. So let's just skip that and go to our main thing, which we want to go to our VSEPR lab again. And when we do the VSEPR lab, which is right here, and it's the one we were looking, no, not that one, sorry. We're doing the VSEPR lab because that's your homework. Sorry, I clicked on the wrong thing. I didn't mean to click on it. I just wanted to be off of it. Okay, here we go. All right, now we got it. All right, so I want the VSEPR lab, which is not here. What? Yeah, there it is. Okay, so this is our class practice. So we're going to look at it. I'm going to download it because that's the best thing to do. And we are going to, I wish I had my answers on here. Okay. Okay, so let's do that. Okay, let's look at it. And for this particular one, we've already done the Lewis structures for all of these. So hopefully we'll remember. But the main thing to remember is what type they are, AB3. Oops, I forgot to say enable editing, which I need to, so otherwise I can't type on it. All right, let's look and see here. All right, here we go. So the Lewis structure for BF3 is a trigonal planar. So we know that. So it's an AB3, okay? And it has three things around it, and they're all bonds. Therefore, the molecule is non-polar. And we're just gonna do these few little things real quick. And it's gonna say non-polar. Oops, non-polar. Okay, we are going to insert a little bit more stuff in here. We're going to do a bond angle here. Let me insert that. I don't know why I gave you guys this one. I meant to give you a different one. Okay, so we're going to insert rows below and insert here rows below too. Okay, so this is going to be the bond angle. The bond angle for this one, well, for this one's 109.5, which is not on there because I did not put it. But for this one's 120 because we have, so it is no resonance, right? And it is nonpolar. So what intermolecular force is IMF? We're just going to call him IMF. Well, the only one, and we said we we're going to call him LDF for London dispersion, right? Remember, this is the only intermolecular force that this can have unless it's charged. If it is charged, then it's an ion and it can induce the other kind, but it's not. So since it's not, we are going to keep going for the next one, SO3. Okay, SO3, if I'm not mistaken, Oh, let me see. What is SO3? I think I've got all of these answers already in my stuff. All right, so here's the VSEPR lab we were doing, and the next one is an AB3 also, which is what I thought, but I want to make sure I didn't want to do all the math again. We've already done that. It's still trigonoplanar. So we're just going to put that there. Oh, and by the way, that goes there too. And it goes there too. And the angle is still 120. So obviously, this one does have Lewis structures, yes. I mean, Lewis structures resonance form, and there are 3 of them because you have one double bond that can move around in 3 different places. And this is nonpolar again. And since it is nonpolar, the only intermolecular force it can have is London. All right, the next one after that, we have a linear. So this is an AB2. And that means it is 2 groups that are on the central atom. Therefore, it is known as a linear. Oh, sorry, I meant to put 3 there. That's a 2, and this is linear again. Linear, okay. And the angle, of course, is 180 because a line if you take a circle divided in 2, you get a linear. Therefore, this is also no resonance, and it is nonpolar also, which means nonpolar. Nonpolar. Okay, and oh, okay, that's what it was. Okay, that's why it was like what? I was like, there we go. That should have gone here and not there. And I should just say no. There we go. All right. Now, next one, of course, is London dispersion. Nothing is charged so far. So far, we haven't gotten anything. Nothing's charged. The next one, however, that is going to be an AB2E2. And in this case, not only does it have the number of electron groups is 4, and this is going to be a bent molecule. Bent. It is charged, and the number of bonded atoms is only 2. Oh, sorry. So that's tetrahedral for this part. Tetrahedral because we have 4 things, but bent because only 2 of them are, yes, exactly. 104.5. The answer is no one here. And is it polar? Yes, it is polar. Now we're going to get a lot of stuff. Always London dispersion, right? We also need dipole because it is polar. And we can also induce an ion dipole since it is charged. Do we have hydrogen bonding? No, because there is actually not a hydrogen in the whole molecule. All right, so let's go to the next one. Water. Okay, so water, we're just going to do the general formula, which is an AB2E2. So we know for a fact that there are 4 electron groups, and that is tetrahedral, right? And two of those groups are bonded atoms, and the molecular shape is bent. We just did this. There are no resonance structures. Oops, it's supposed to be no. And oh, we did not add the angle. Okay, I need to add both of those to this one again. All right, let's add. No, insert rows below and insert rows below here too. So we can add these 2 things. We don't need all this. All right, so the bond angle is 104 water. And it is polar, yes. And the IMF and intermolecular forces are going to be London dispersion forces, dipole, dipole, right? Ion dipole, because if you were an ion, you could be inducing one because you have a dipole. So yes, you can do an ion dipole. Well, actually, yes, because it is a molecule. And yes, we do have hydrogen bonding also. So this one has all four. Next one we have is SO4 negative. So with SO4 negative, we have a plane AB4, which means we have four of those. I'm just going to copy this word. It's easier. And all four of them are going to be bonded. This is also tetrahedral. The bond angle is 109.5. There are no resonance structures. Is it polar? Yes, it is non-polar because we do not have a difference. There are no lone pairs. So no lone pairs, that means that the 4 and the 4 are the same. See here, you have lone pairs, you have 2. So there you have 4 and 2. Okay. And then since it is nonpolar, you're going to see London dispersion, but it is a charged molecule, so it is capable of inducing an ion dipole. Okay. Next, we have the other one, which is NO2 plus. NO2 plus is an AB2 because it is linear. So you have two of these. It is going to be linear. Also 2 again. So that is definitely a nonpolar. And this angle is 180. There are no resonance structures because there are no double bonds. And it is a nonpolar molecule. Therefore, the only things that we can do is London dispersion. Oh, London dispersion force. And we have also ion dipole because it is charged. All right, next one that we have is PO43 negative. That one is going to be an AB4. Oh, where's my 4? There we go. There are 4 of these. The name of it is tetrahedral. We have 4 of those. Once again, this is tetrahedral, so it doesn't change. The angle is 109.5. There are no resonance structures. It is a non-polar, but since it is a charged molecule, you can have London dispersion forces because it is a molecule, but also ion dipole because it is as you can see, it's a charged molecule. The rest of these are charged, so NO3 negative. Now, NO2 positive, NO3 negative, they're going to be different. So this is AB3. This one is going to be 3. So that means this is a trigonal. Oh, I don't have one of those. Trigonal planar. All right, since it is a trigonal planar molecule, we are going to copy that because that's what this is, because we still have 3 bonded atoms. Now, do we have resonance? Well, we have 120. Yeah, we do have resonance. We have 3 of them because they can move. It is non-polar, but it is charged. So once again, London dispersion force and ion dipole are the 2. All right, that's that one. We have 10 more to do, and we will go on. Now, I would sort of wish that you guys would do them yourself, but why don't you pause the video and give you a little while, give you about 15 minutes, and try to do the rest of this page. I'm going to go ahead and keep going, but you need to pause now. And when you resume, I'll be back showing you how to do the next one, right? AB. So in this case, the next one is CO3 2 negative. So that is an AB3. Once again, number of electron groups is 3. That makes it a trigonal planar. This is 3 also. That makes it a trigonal planar. We do have resonance. We have 3 of them. Is it polar or non-polar? Oops, you know what? I need to add one more thing on here. Here we go. See, I always forget to insert these things. Insert. Oh, no, not there. Insert here. I need another column because we need to put the bond angle. And in this case is 120, right? And there are no resonance. I mean, yes, there are polar or non-polar. Sorry, I'm trying to get this one out of here and insert one last column down there. And I mean row, and call it IMF, right? Okay, so in this case, it is non-polar. Once again, so we have London dispersion forces, and we have an ion dipole because it is a charged molecule. Next one, we have SO2, and this is not a charged molecule, but it is an AB2E. I know, right? It's like surprising. Why is it an AB2E? Because you have one lone pair, but 2 bonded atoms. So this is a 3. So therefore, that would be the official not molecular, electron group geometry, but there's only 2 of those that are bonds. Therefore, this is bent. But in this case, this bent is going to be less than 120 degrees. And how much less? Well, yes, there are resonance structures. In this case, we have 2. All right. And is it polar? Yes, it is. Why is it? Oh, sorry. We need to put polar. Not yes. And that means we have a lot of stuff here. We have London dispersion force. Yes. We have dipole because we are polar, and we have ion dipole because we are charged. And the fact that we are polar also can induce an ion dipole. So in ourselves, no, but we can induce one because we are charged if we had an ion around. So that's a little bit harder to describe. All right, the next one is NO2 negative. And in this one is another AB2E, which means that we have 3 things, and it is a trigonal planar, but 2 of them are bonds, only 2. So there is a bent structure. Once again, less than 120 degrees. Do we have any resonance? Well, yes, we do. And we have 2 again. All right. And this molecule is polar because we do have a lone pair. And that means the London dispersion forces, dipole, dipole, and ion dipole are the only ones. There are no hydrogens. So you notice I'm skipping the hydrogen bonding altogether because so far we haven't had any hydrogens. Next one is PF3. This one's a little different. This is an AB3E. Why is it? Okay, that means we have 4. We have tetrahedral here. But only 3 of those are bonds, which makes it a trigonal pyramid. Sorry, pyramid. There we go. when you look at that, that means that your bond angle is 107. Do we have resonance for PF3? No, we do not. Is it polar? Yes, it is. Why? Because, like I said, it has a lone pair. Therefore, you have London dispersion forces, like all molecules do. Dipole, 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 dipole. And if you had an ion around you, you could induce an ion dipole since you are polar. Next one, and coming up is silicon tetraiodide, and that is an AB4, which means it has 4 things around it, 4 areas of electron density, which makes it tetrahedral. And there are no lone pairs, which also makes this tetrahedral. That means we have a 109.5 angle. There are no resonance structures. It is nonpolar. And oops. Okay, I keep doing that. Control X. Okay, nonpolar here. And the only 2 things that it can do is London dispersion force. Actually, the only thing it can do is London dispersion force because it is not charged and it is nonpolar. So none of those. All right, next set that we have is this and our last. Let's get inserted columns in here. I mean rows in here, and insert one more down here. Let me get rid of these first though. Oops. All right, and insert another row here. Okay, and here we go. So this is bond angle again. And the other one is intermolecular forces. Okay, so let's look at you. All right, what are you? You are last 5 and NH3. So this is ammonia. Ammonia, the general formula is going to be AB3, oops, AB3E. Because we have 4 electron groups, therefore we are tetrahedral, oops, no, sorry, tetrahedral. Just, that means we have 3 bonded atoms, which gives our molecular form of shape of trigonal pyramid. That's what ammonia is, which the bond angle is 107, sorry. And there are no resonance. It is polar. Therefore, here we go. This one we have London dispersion forces. We have dipole, dipole. We could induce an ion dipole. And we also have hydrogen bonding because it is nitrogen bonded to hydrogen. All right. The next one after that, and I wish you could see them all, but there it is, NH3. The next one is H3O plus, and that is an AB3E again. So pretty much everything we've said about this other one applies to this one. As a matter of fact, I'm going to copy everything. I mean, why reinvent the wheel, right? If I can just copy it. And we go 3 here, 107 here. That one's easy enough for me to type. And no, it's also easy for me to type. And there are no resonance structures here either. It is polar, that's easy enough. But all of these also apply. And this time it is an ion. Therefore, ion dipole definitely applies to this one because it is the ion itself. All right, the next one is NH4 plus. Now, this is funny because this is an AB4 because it has 4 things. So the molecular geometry is tetrahedral. I mean, no, not the molecular, sorry, the electron group geometry is tetrahedral, but also the molecular geometry. The angle is 109.5. There are no resonance structures. It is not, okay, no. I clicked on you This is what's going on. I don't click hard enough. Okay, since it is non-polar, all you can have is London dispersion forces. You cannot have dipole-dipole, you cannot have ion dipole, and definitely not hydrogen bonding. However, ion dipole, yes. Sorry, ion dipole, yes, because it is charged. SO3 negative is an AB, 3E also. That means we have 4 things around it. They are tetrahedral, 3 of them, and that means this is a trigonal pyramid. So we're going to copy that one. And the bond angle is 107. There are no, oh wait, this does have resonance structures. No, wait. No, not SO2 negative. No, SO3 negative does not. No, no resonance structures. It is definitely polar because we have one lone pair in the sulfur. So you've got London dispersions and dipole, dipole. And since it is charged, it can also induce an ion dipole. And it could induce one anyway because it is polar. So all of that. The last one, and I want you to pay attention to it, says CHCl3. So one of these is not like the other, even though it's an AB4. And there are 4 things around. And we know this is tetrahedral. All of this is going to be looking like it's non-polar, but I'm going to show you why it meets that requirement. Angles 109.5. I don't know if you've been noticing, but so far everything that's 109.5 has been non-polar. So no resonance structures. It is polar though. Why is it polar? Well, let's first figure out what we have here. London dispersion always. Dipole, dipole for sure. We are not charged, so there's nothing else. All right, so these are, oh, and yes, you could induce an ion dipole also because you are a polar molecule. So if you put, so in the solution, you added an ionic compound, it would definitely dissociate it into its ions. All right, so that's all of them. Now, let me show you why CHCl3 is polar. Here's the polarity piece. Okay, the last piece of information is the distribution of electron density and charges around the molecule. Molecule with a uniform distribution of electron density is nonpolar, and one with a symmetrical distribution is polar. A molecule is nonpolar only if it has no lone pair electrons about the central atom, which it didn't, and all groups attached are identical. That is the one thing that it is not. They are not identical. We had 1 hydrogen and 3 chlorines. So you notice it says both conditions must be met to be nonpolar. So there you go. In this case, it is polar. And that concludes this part of the lecture. Now we're going to go on and complete one more thing, which is the, let me save this. Answers. I'm just going to put it answers. Okay, save it. All right, once we do that, we're going to look at the next part, which is, like I said, the properties of water. Properties of water are very interesting because this molecule of everyday things that you already know is a very important, no. I said, no. What are we doing here? No. What? Where is it? Oh, I have lost it. Okay, no. Oh, there it is. That's not what I wanted. Okay, no, go away. Okay, so I did not want the lecture. I just wanted to go to the module. Okay. Is it gonna go there? Yeah. All right, so properties of water, that's what we start this one with. Because of the properties of water, there are many things that water can do. And that's the main thing about this. We need to know these. And water is known as the universal solvent. Now, it's not truly a universal solvent, but it will dissolve most things. However, oil is not one of them, is it? So let's look at this PowerPoint. Okay, so the first question that we have is, should we control a chemical that causes excessive sweating and vomiting? Well, yes, of course. It's a major component in acid rain. Acid rain is no good, right? Can cause severe burns in its gaseous state. So that means as a vapor or whatever it is. Accidental inhalation of it can kill you. Definitely don't want that. It contributes to erosion. Ooh, that's not good either. Takes the topsoil. Decreases the effectiveness of car brakes. It has been found in tumors of terminal cancer patients. What is this chemical? The name of it is dihydrogen monoxide, aka H2O or water. Yes, all of those properties, all of those things that you read about is what water does. Now, some things are good. Notice it said excessive. And yes, it can kill you if you drink it. And definitely if you inhale it, because that's called drowning, right? All right, so let's look at what is the molecule that is the most common in living cells. The answer is water. Most cells are anywhere from 70 to 95% water, depending on what cell you're, which type of cell. The water planet, that's where we live, right? The Earth is pretty much mostly water. So it is a good thing to, don't worry about that part, to know what the properties are. Well, one of them is cohesion. Cohesion means that water likes water. That is due to its hydrogen bonding because of the molecule being polar. There it is. Okay. Next thing, water is adhesive. That means water will stick to other polar things, to other charged molecules. Why is that? Once again, because of the hydrogen bonding. Water can be used to transport, water does the transport in trees. And remember, the roots are way down there and the leaves are way up there. So in order to do this, water has to defy gravity. How does it do that? By using both adhesion and cohesion. Water also has a high surface tension. Notice this little bug over there is pretty much walking on water. Why is it walking on water or standing on water? Because water has a high surface tension. That means that the surface of it is hard to break. Have you ever belly flopped into a pool? Yes, my point exactly. Water shouldn't be so hard on you. It should just get out of your way, right? Because water is liquid. Well, because of its high surface tension, it feels like you're hitting a brick. And it could even break your bones, depending on the height and speed and the mode of entry too. That's why when divers dive, the professional divers dive into the water, they either do so with their fingertips or their toe tips. Once that is determined, is once again, it is hard to break it because of the same reason, hydrogen bonding. Hydrogen bonding accounts for all the properties of water, as you probably have guessed by now. Water has a high specific heat. What does that mean? That means that it takes a lot of energy to raise the amount of heat. It takes a lot of heat to raise 1 gram of water 1 degree Celsius. Due to the hydrogen bonding, water acts as a larger molecule. Usually larger molecules have higher specific heat, but water is a tiny molecule, yet it acts like a large molecule due to that. What is heat? Well, we know heat and temperature already, so let's just remember it is a quantity of kinetic energy due to molecular motion. Temperature is a measure of that average speed. Okay. Celsius scale is really usually what we use, and these are the freezing and boiling points of water, and also our normal temperature in Celsius. Water also does another thing, it stabilizes temperature, because water can absorb and store a huge amount of heat from the sun. The planet that we live on is livable because it moderates our climate. And organisms such as ourselves and everything else are able to survive those temperature changes because water moderates it. Water also has a high heat of vaporization. What is that? Well, it is the quantity of heat a liquid must absorb for 1 gram of that liquid to convert into a gas. All right, so it's very hard. So it needs a lot of heat. So if it absorbs a lot of heat, of course, that's going to go up, and yes, it's going to evaporate. Therefore, this is another mechanism that water is a part of. This is known as evaporative cooling. When you sweat, your body heat is absorbed by the water and it evaporates. Therefore, your body heat is reduced because of that. Water cools your organism from excessive heat buildup. Once again, hydrogen bonding. Water expands when it freezes. I don't know if you've ever noticed, but ice floats, it doesn't sink. Anything else sinks in its own solid. So if you have solid water, which is ice, it floats. That's because the distance between the molecules increases from the liquid to the solid form due to the hydrogen bonding. Therefore, it becomes less dense than the liquid, so it floats. And there it is. See, look at that. Water in its liquid floats. Water in its liquid, ice in its liquid floats, and frozen benzene in its liquid state sinks, which is what you would expect. And of course, you know the states of matter. Now, one of the things that is amazing about this, the reason why it's a good thing that water does expand, it helps you keep the aquatic life living under the ice. Because if it froze from the bottom up, these critters would also be frozen in the process. Instead, water freezes from the top down. And yes, it can be fully frozen, or at least it looks like it. Water is a versatile solvent. And that's what I was telling you. It's called the universal solvent. It will do a solution very quickly with almost anything that is polar, or almost anything, no, anything that is polar or ionic, right? Now, some things do not dissolve as easily in water, but that's another thing. And definitely not nonpolar substances like oil All right, a solution, we know about a solution, solvent, we already talked about that, blah, blah, blah. All right, so materials that are capable of dissolving in water are called hydrophilic. Hydro meaning water, philic meaning loving, water loving. If you do not dissolve, that means they have no polar region. But if you do dissolve in water, that means you're hydrophilic. Therefore, you have a polar region, such as sodium chloride. We already looked at this picture. Remember, this is called solvation when the water, well, actually hydration, because this is water, surrounds the particles of the ions of an ionic compound. All right, this is called also hydration, and in this case, it's connected to a protein. Hydrophobic, on the other hand, they repel water. Do they repel water? Hydrophobic is fearing, water fearing. Therefore, they have non-polar covalent bonds. For example, lipids, which I keep saying, oils. And that's it. We are not going to talk about solution concentration because that's for next class. And just so that you remember, all these properties make water a very versatile type of solvent and a very wonderful thing for us that we have water on this planet. Otherwise, we could not live on it. Neither could any other organism. So there you go. That is the end of our lecture for today, and you all have a wonderful weekend. Bye.